The Cosmodromer. Most people living in the year 3026 do not actually understand how the DM ramjet drive works, beyond knowing that it involves a field which, when it passes over dark matter particles, transmutes them into some other weakly interacting particle with a great deal of momentum perpendicular to the field. The field generator itself predates the drive system by more than a century. For decades, nobody noticed that generators were pushing very slightly against their mountings in laboratory tests. Had the effect worked on ordinary matter, it would have been the ultimate power source. As it was, futurists eventually realized its true value, the ultimate interstellar spaceship drive, at least for ships of a certain size. When a ship carrying the field moves through dark matter, thin but roughly evenly distributed throughout the Milky Way, it gains a steady forward boost. While an almost entirely harmless plume of weakly interacting rocket exhaust streams out behind it, a field generator about as wide as a large moon can push a 10,000-ton ship into genuinely relativistic flight in about a year of ship time, though about a year at a light speed at 1G is only a loose low-speed rule of thumb. In practice, as you get nearer light speed, the rule of thumb bends hard. A little over a year of comfortable 1G acceleration gets you in the neighborhood of Gamma 2, around 86.6% of light speed. Push you on towards Gamma 10, around 99.5% of light speed, takes almost 3 ship years by acceleration leg and nearly 10 years by outside clocks. Cosmodromer is a skyscraper with an engine, but with no onboard fuel beyond the modest nuclear reactor used to power life support, and the conventional thrusters need to reach the minimum speed where the DM ramjet becomes effective. Stopping is more complicated. To slow down, the ship first scoops up a large quantities of ordinary matter, using it to bleed off velocity before flipping to the field. That collected material then serves as propellant for in-system maneuvering once the drive has brought their speed back down to something more reasonable. About half the ship's mass is the ultra-thin ring that generates the field, along with the graphene tether that connects it to the main hull. Viator Macroporos doesn't have any real idea how the DM ramjet works either. He's just crew aboard the Cosmodromer, the 10,000-ton relativistic starship that first arrived in his colony system of Pollux 5 years ago, only a few years after news of the drive's existence reached them from Earth. The engineer has tried to explain it to him during assigned maintenance shifts, but Viator's eyes tend to glaze over whenever the conversation drifts into conservation of momentum, or how at extreme velocities the thrust produced by intercepted dark matter begins to balance out against the drag from stray atoms of ordinary matter and blue-shifted background radiation. What Viator understands is simpler. The big orange giant he was born around was not where he wanted to spend his life. When Cosmodromer arrived from Earth for resupply, upgrades, and help installing technologies invented since their departure, there were surprisingly few volunteers for the next mission, probably because they were being sent to hunt down a colony arc ship that had left Earth several centuries earlier, bound for the triple binary star system of Castor at a far slower speed. All he knew was the only requirement, besides some guts and brains, was the usual note you saw at any spaceport that asteroid and comet miners visited. Have spacesuit, will travel. And Vitor, who grew up welding spaceship hulls, had a spacesuit and a will to travel. The full journey from Earth to Castor would have taken over half a century by Earth clocks, though the detour through Pollux added surprisingly little time, since Pollux and Castor are close neighbors by interstellar standards. From Pollux, the interception run would take under a decade of ship time if they did not spend the whole voyage at a full Gamma 10 cruise, or a little over that if they accelerated and braked more gently at 1G. Either way, it was absurdly fast compared to the arc ship they were chasing. Their job was straightforward: slow to rendezvous, transfer equipment and crew from the vastly larger vessel, assist with early colony setup at the destination, then move on to the nearest star system capable of resupplying them before receiving whatever mission come next. Arc ships were simply too big to be retrofitted with such drives, and the engineers all said the sweet spot for useful ships with this system was 100 to 10,000 tons, but that nothing less than 1,000 tons would permit any real crew complement. So it was ships like the Cosmodromer and a lot of 100-ton probes, and Vitor had been told they were sending out thousands every month from the mega shipyards of Luna and Neptune, and that many hundreds of vessels like the Cosmodromer had been commissioned for these types of missions. The planners back on Earth claimed this assistance would shave decades off colony development. Vitor had been told that many such ships had been commissioned, one for each ARC ship or ARC fleet that could plausibly be reached in time to offer assistance. Vitor doesn't care much about that. For junior sailor Macroporos, it was simply a chance at a life of adventure. He hasn't fully internalized the fact that once Cosmodrome settles into a Gamma 10 cruise at about 99.5% of light speed, every day aboard the ship corresponds to roughly 10 days passing the outside universe, where everyone he ever knew back home is aging 10 years for every one he does. Getting to that speed is not the old 1 year to light speed shortcut though. At 1G, climbing to Gamma 10 takes almost 3 years aboard the ship, nearly 10 years by outside clocks, and almost 9 light years of runway. Then you need to pay that time bill again to slow down. The engineer mentioned that once they clear this denser region of space, Cosmodrome could go even faster with less drag, but that would require thicker radiation shielding. Vitor knows his grandparents reached Castor aboard one of those enormous, slow arc ships themselves, aging through centuries of travel. By contrast, the crew of the Cosmodrome might experience less than 5 years of subjective time during the full relativistic cruise portion of a trip like this, though the acceleration and braking legs can easily make the whole voyage closer to a decade aboard ship. He's always wanted to see the inside of one of those behemoth arc ships for real, not just some virtual reality sim, but he can't imagine spending centuries on one for a single voyage, compared to years or a decade aboard one of these new ships. That, he's been told, is more or less the norm now. About 2.9 years of ship time to climb to Gamma 10, about 9.6 years the outside universe, and the same to slow down again. The middle of the trip is the easy part, cruising at a hair short of light speed, while the crew experiences only a tenth as much time as the outside clock records. For many nearby stars, you don't even bother reaching Gamma 10. You accelerate halfway, flip over, and break the rest of the way. But to Vitor, it just feels like a better way to travel than his ancestors ever had. Life aboard a relativistic starship. Welcome to Science and Futurism with Isaac Arthur, for another installment in our loose series on life in the future, where we looked at everything from life on board an interstellar colony ship to serving as a planetary governor. In this series, we tend to approach these topics from the perspective of one or more fictional characters, to get a sense of what life in these situations might actually be like, not just the technical specifications and plans for moving people through space or selling them on new worlds. Once you leave the realm of slow travel, relativity stops being an abstract curiosity and becomes a daily logistical concern. On a relativistic starship, time itself becomes a managed resource, just like oxygen, power, or reaction mass. From the crew's perspective, life aboard ship feels mostly ordinary. Days are still 24 hours long, meals are eaten on schedule, maintenance cycles repeat, and watches are stood. What changes is not how time feels locally, but how the ship's calendar relates to the rest of the universe. A relativistic crew does not feel their own time slowing. Their clocks, thoughts, and metabolisms all run normally. The shock comes later when they compare calendars and discovers that far more outside history is accumulated than shipboard time. Messages become strange too, though not always in an intuitive direction. If the ship is racing away from home, live signals from behind are stretched out and redshifted, arriving slowly and thinly. The bursts usually come from relays, destination archives, or stored data dumps picked up during deceleration or arrival. A single packet might contain years' worth of recorded updates, births, deaths, promotions, political upheavals, and entire careers unfolding between one log entry and the next. Replies sent with care and deliberation may not be read for decades of external time. A relativistic ship is never truly cut off from civilization, but is permanently out of sync with it. This has profound cultural consequences. Crews aboard relativistic ships tend to skew too young and single, not because the ship requires youth, but because youth is more tolerant of temporal dislocation. In many ways, that's like every sailor signing up since the age of sail. A 30-year-old signing up for a 10-year shipboard tour knows they may return to a civilization that's aged 70 or 80 years. A 60-year-old signing the same contract might never see a familiar world again. Even with life extension, the psychological weight of temporal separation matters. Careers are shaped by this as well. A junior sailor might leave home as an unknown apprentice and return decades later by Earth clocks to find they were rich from compound interest on their pay, and that the nieces or nephews they left behind as toddlers were now great-grandparents. Or, if they helped bring colonists or need help to a new colony, to find their names attached to ships, institutions, or entire colonies they barely remember helping to found. Conversely, a relativistic crew member can watch political systems rise and fall without ever experiencing them personally, becoming living relics of earlier eras. Family ties stretch and thin. Relativistic travelers tend to think of relationships not in years but in exchanges, messages sent, replies received, milestones acknowledged. Even if they live ultra-long lives with advanced medicine, it's hard to keep in contact with someone experiencing so much time in transit and so differently. Some families probably adapt, treating relativistic service as a kind of extended absence. Others quietly drift apart, separated not by distance but by time flowing at incompatible rates. From the outside, relativistic crews appear almost frozen in time, their aging slow to a crawl. From the inside, they are the ones watching the universe rush past. Though, paradoxically, when they look at a planet while traveling at those speeds, they see the planet having its clocks go slowly. And sometimes they might be literally frozen in time as well. This whole time I've been assuming the crew is awake and active, but this disconnect from time can become even more stark if they decide to sleep in some sort of hibernation or suspended animation. It might be even more jarring to wake up and discover you missed decades or centuries of messages all at once, and you watch a loved one's entire life fast forward without any influence from you. Relativity without the chalkboard. All of this comes down to one deeply unintuitive fact. At high speed, it isn't just mass that resists being pushed, it's total energy. At everyday speeds we can ignore that. Your rest mass energy, the famous E equals mc squared, is so enormous compared to everything else that we treat mass as the whole story. Heat, chemistry, even nuclear reactions are tiny ripples on top of that ocean. But as you accelerate toward light speed, kinetic energy stops being a small add-on and becomes a major fraction of what you are. The faster you go, the more energy you have, and that energy itself behaves like inertia. You aren't just pushing the ship anymore, you're pushing the ship plus all the hard-won motion you've already paid for. There's a useful marker at about 86.6% of light speed, or gamma 2. At that point, your kinetic energy equals your rest mass energy. Half of your total energy budget is now motion. Beyond that, most of what you're hauling forward isn't steel and air and people, it's the momentum you've accumulated. The number that keeps score is the Lorentz factor, gamma. Gamma tells you how the universe slices up time and distance for something moving fast. If gamma is 2, the traveler experiences 1 second while 2 seconds pass for someone at rest. If gamma is 10, the traveler experiences 1 year while 10 years pass outside. That's the regime a true relativistic starship aims for. Around 99.5% of light speed, gamma hits 10. Once you're cruising there, the ship's point of view changes dramatically. 100 light years of cruise can feel like 10, but you still have to budget the acceleration and braking legs, and those are not small. At 1G, reaching gamma 10 takes about 2.9 years aboard ship, about 9.6 years by outside clocks, and covers about 8.7 light years. Stopping takes the same again, so for a star 100 light years away, if you accelerate to gamma 10, cruise, and decelerate at 1G, the outside universe sees a voyage about 102 years, while the crew experiences about 14 years. Neither description is more real than the other. They have the same geometry viewed from different frames. And this isn't just a clever thought experiment. We see it in particle physics all the time. Fast-moving particles that shoot decay almost instantly survive long enough to cross detectors because, in their own frame, less time passes. In a more mundane example, GPS satellites have to correct for relativity too. Their orbital speed makes their clocks tick a little slower, while being higher in Earth's gravity well makes them tick faster by a large amount. The net result is that GPS satellite clocks run fast, by about 38 microseconds per day unless corrected. Or maybe it's better to say Earth runs slow by that amount. So for relativistic travelers, the consequence is simple. The faster you go, the more the universe's future you skip over. You miss a lot on the way to the stars, but that's not a bug, that's a feature. The Propulsion Wall. If relativity makes interstellar travel attractive, propulsion is what makes it difficult. The fundamental problem is the rocket equation. Any ship that accelerates by throwing mass out the back must also accelerate the fuel it hasn't used yet, including the fuel it will need to slow down later. This creates an exponential penalty. Double your desired speed, and you need far more than double the fuel. This becomes especially brutal at relativistic speeds. If your exhaust velocity is low compared to the speed you want to reach, you quickly hit a wall where nearly all your ship's mass must be fuel, leaving little room for payload, crew, or structure. Chemical rockets, ion drives, and even most nuclear propulsion systems simply cannot push payload carrying ships anywhere near relativistic speeds. Our made-up drive for today, the dark matter ramjet, sidesteps this problem by finding its fuel along the way, as a clear hat tip to the classic Bustard ramjet, the idea of using a fusion drive that scoops up hydrogen as it travels. The difference is that dark matter is far more evenly distributed than hydrogen, and, if usable at all, would not produce a powerful and dangerous rocket flame out the back. How anything like this could actually work remains a complete mystery, especially since dark matter itself is still poorly understood. For those tuning in looking for ideas for science fiction novels or games, feel free to steal this concept. Just keep in mind that deep space contains very little actual matter. You need an enormous collection area to make it viable for a small ship, which is why you can't power whole civilizations this way or send mega armadas. Only by sweeping up material with a catcher the size of a planet, moving at relativistic speed, do you gather enough mass to drive even a large ship, one that's quite small compared to the USS Enterprise D for instance, and that itself is still tiny compared to what an arc ship would require. Thus it makes great ships for a space opera. Anyway, conventional fusion improves matters, but not enough. Fusion reactions convert only a small fraction of mass into usable energy. Even optimistically, fusion exhaust velocities cap out at a few percent of the speed of light. That limits practical ships to perhaps 10 or 15% of light speed, well short of the relativistic regime where time dilation becomes transformative. We will deep dive that and the potential speeds of other systems in our upcoming Starship Drives episode. The other half of the problem, though, is deceleration. A ship that accelerates to high speed must also slow down. Carrying separate fuel for braking effectively doubles the energy cost. This is why missiles can outrun colony ships. Missiles do not need to stop. Same for flyby probes. Any propulsion system that allows free, or nearly free, braking is revolutionary. Magnetic sails, particle scoops, beam deceleration, or even interactions with the interstellar medium can all reduce the enormous energy cost of slowing down. Even weak braking is valuable, because it lets a ship spend all of its carried fuel on acceleration instead of saving half for stopping. There's an irony here. The Bustard ramjet, often cited as a failed idea, may actually work best as a brake. The math suggests it produces net negative thrust at high speeds if its large magnetic field were reversed, meaning it can't push a ship to arbitrarily high velocity, but it might slow one down for almost free. That was the basic idea behind the famous ship in Tau Zero. The eternal fuel-free acceleration, that is, not the deceleration. Even there, physics pushes back. At extreme speeds, everything you run into, interstellar gas, dust, even relic photons from the early universe, begins to generate drag against your thrust. You hit a terminal speed set by ship design and environment, and even with time dilation on the order of 100, a day aboard might equal months outside, but crossing a galaxy would still take centuries to millennia of ship time, depending on the route. Intergalactic space helps, being emptier, but the cosmic microwave background is everywhere, and still pushes back. And since dark matter does clump around galaxies, our DM ramjet we invented for this episode is less useful in intergalactic void where there's less dark matter. This is why most plausible relativistic propulsion concepts either avoid carrying fuel altogether or use exhaust that already travels at or near light speed. Photons, neutrinos, or antimatter byproducts. Only when your exhaust approaches light speed does the rocket equation finally loosen its grip, and even then, never fully lets go. And that is where the truly strange engines enter the picture. The engines that can actually go relativistic. Once you accept that carrying your own reaction mass is the core problem, a list of viable relativistic propulsion systems narrows down dramatically. To get close to light speed with a ship large enough to carry people, you either need exhaust that already moves at or near light speed, or you need to avoid carrying fuel at all. Antimatter is the most straightforward example. When antimatter annihilates with normal matter, nearly all that mass involved is converted directly into energy, typically released as extremely high energy photons. That makes antimatter the ultimate high exhaust velocity fuel, at least in principle. A photon rocket, whether powered by antimatter or some other energy source, has an exhaust velocity equal to the speed of light. That does not mean such ships are easy to build. Gamma rays are not friendly exhaust. They are extraordinarily penetrating, difficult to reflect, and catastrophically destructive if misdirected. Still, antimatter remains compelling because it neatly sidesteps the energy density problem. If you are willing to accept absurd energy budgets, antimatter can push large ships to relativistic speeds. See our recent episode on antimatter propulsion for a deep dive. Black hole drives occupy a similar conceptual space, though they are even further from current engineering. A small enough black hole radiates enormous amounts of energy via Hawking radiation, effectively acting as a mass-to-energy converter. If you can feed it carefully, you have something like a boosted ramjet for energy itself, with no intrinsic upper speed limit imposed by carrying fuel. If the interstellar medium is too thin, or if you want to accelerate with your black hole harder, then you may have to pack several thousand tons of regular mass propellant. If you cannot feed it, it behaves more like antimatter, limited by how much mass you are willing to bring along in the form of black holes stored in your engine room. A wormhole, which is a quasi-black hole that had its other end inside a star or a different younger universe, might make an awesome endless fuel drive, and one may be dense enough to let you achieve gamma well above 100. Vacuum energy, which I mentioned before, if it proves usable, will be even more exotic. If spacetime itself contains extractable energy, then propulsion becomes limited only by how quickly you can couple onto it. That would fundamentally change not just relativistic travel, but civilization as a whole. For now, vacuum energy remains speculative, but occupies an important place in the taxonomy of engines that break the usual rules. Another entire category of relativistic propulsion avoids onboard fuel entirely by borrowing momentum from the universe itself. Bustard-style concepts attempt to scoop up interstellar matter and use it as a reaction mass, and again these struggle at high speeds because drag rises faster than thrust from all the wide-mouthed scooping, but they illustrate the underlying idea. If you do not carry your fuel, you do not have to accelerate it. The fictional DM ramjet that Vitor's ship uses fits in this category. It replaces ordinary matter with dark matter, which would be passing harmlessly through any part of your ship that wasn't the drive, and thus creates far less ordinary scoop drag, which is why I like it. And since the exhaust is weakly interacting particles that are also loosely scattered through the galaxy, it gets around a lot of the issues of civilizations having giant ships or huge numbers of ships that are all planet-buster weapons if set to ram something, but the conceptual advantage is the same. The most mature and arguably most realistic version of this approach is beamed propulsion. Instead of carrying fuel, you are pushed by energy sent from elsewhere. A powerful laser array, particle beam, or even a stream of macroscopic pellets can accelerate a ship across interstellar distances. The ship itself becomes more like a train than a free-roaming vessel, tied to an infrastructure network that supplies energy from behind. We deep dived these recently in Interstellar Relays if you want more details. Now, this has drawbacks. You cannot easily change course. You are dependent on distant infrastructure, but it also has enormous advantages. Beamed propulsion neatly solves both acceleration and deceleration, since the same system that pushes you can also slow you down. It allows ships to remain relatively light, as scales well with civilization-level energy production. They move the hard part of the problem off the ship and onto stationary infrastructure, where mass, cooling, and redundancy are easier to manage. They also, ironically, are the one most civilizations would feel safer with, which sounds strange as it means you're placing massive mega lasers all over the place, but they are safer to the owner than a spaceship able to generate those same kind of energies, and indeed such a ship being self-propelled must generate far more. If you don't like the look of an inbound beamer ship that you're slowing down, you can always simply vaporize it with that laser instead. One other quasi-solution worth making a quick note about is that you might be able to build a Alcubierre drive or warp drive that runs slower than light, just up to the speed of light rather than passing it. This would still have all the same exotic matter requirements like negative matter, but it wouldn't cause any problems with causality. Also, it is the only option that would not cause time dilation on board, due to the ship being in a flat warp bubble. You and your destination's clocks won't quite match, but at least you can still use the same calendar. Anyway, that ship coming from another solar system is passing by your huge laser stations, and reliant on them and getting scanned and looked over by them, whereas otherwise you have some unknown ship entering your space, carrying a doomsday weapon worth of energy simply by moving. That ship from our intro, the Cosmodromer, at 10,000 tons and a gamma of 10, is very small by interstellar spaceship standards, especially compared to an arc ship, which might mass 1,000,000 times that, but it's carrying around 10 to 25 joules of energy, the equivalent of a couple billion megaton nuclear bombs, or a few dozen of the asteroid we think took out the dinosaurs. And that's part of living in a relativistic starship. You will never exactly be entirely welcomed when you arrive, because it's not just how much energy you have if you slam into something, it's how little time they have to react to it. Some giant arc ship going 10% of light speed still have more energy than the relativistic ship did, but they have a huge window of time to spot that ship and deploy defenses, and wreck it far from their population, where scattered remnants are less of a problem. They could potentially even send Marines in to board it, and you would probably want to try to salvage and redirect that ship if possible, For one thing, a broken up ship approaching a Dyson swarm might, if encountered too late, be like a shotgun blast to the whole thing, but Kessler syndrome is not an issue for more diffuse Dyson swarms, even the more compact kinds around dimmer red dwarfs. But it's still nothing a Cartership 2 civilization will casually shrug their shoulders at either. The hazards of going too fast. Even if energy were free and engines perfect, relativistic travel would still be dangerous. Killing a relativistic vessel is fairly easy if you know where it's going to be, and it is a hard time spotting dangerous materials in time to do anything. At everyday speeds, space is effectively empty. At relativistic speeds, it is not. A single atom drifting between stars becomes a high-energy particle accelerator experiment when you hit it at 99% of light speed. Individually, these impacts are manageable. That's literally what cosmic rays are, but collectively they add up to continuous radiation exposure and drag. At moderate relativistic speeds, gas and dust are of greater concern. The cosmic microwave background is also blue shifted in the ship's frame, but at gamma 10 it's still only being pushed up toward infrared wavelengths. At much higher gamma, especially hundreds, thousands, or more, that background glow becomes a serious radiation and drag problem of its own. Starlight ahead of you blue shifts too, and high-energy cosmic rays become nastier still. A grain of sand might contain quintillions of atoms. At truly relativistic speeds, even tiny dust hits like high explosives, and a large grain or a small pebble can carry energy in the tactical nuclear range. Detecting in time is extraordinarily difficult. Try spotting a single grain of dust as far away as our own moon, and remember that at high relativistic speeds, you've got on order of a second to react. Evading it requires either immense maneuverability or active defense systems capable of vaporizing or deflecting incoming particles at extreme ranges. This is why relativistic ships cannot be fragile. They require thick forward shielding, sacrificial structures, or extended sails placed ahead of the main hull to absorb impacts. They need forward shielding, maybe even a thin sail in front of them that can suck up and scatter the hits that you push ahead of you with a beam. These structures can be repaired, recycled, or replaced, but they add mass and complexity. The faster you go, the heavier and more robust your ship must be. It also places a practical limit on how small relativistic ships can be. Nanotechnology does not help much here. Nanomachines are even more sensitive to radiation damage than biological tissue. A pencil-thin probe traveling at near light speed is easy to imagine, but hard to make work. And why bother anyway? If your probe can build whole worlds of infrastructure on arrival, it can instead eat some 100-ton rock-up in your own solar system before departing to make a more robust ship for the trip. All of this conspires to make relativistic starships large, armored, and conservative in design. Speed alone does not make you safe. In many ways, it makes you more vulnerable. Now, this would seem to imply large crews, but while they might be able to carry a lot of people and cargo, they probably do not really need to. Automation is presumably better than now, and there's not much work to do while cruising through the void, and there's a lot of time to do it in. The novel Revelation Space gives us a glimpse of a ship of epic proportions, the nostalgia for infinity, that can carry hundreds of thousands of frozen colonists or a similar amount of cargo, but has a crew of just 5 or 6, and they spend most of their time on ice themselves, waking just months out when deceleration will soon begin to do some maintenance and check incoming radio transmissions to get an idea what the current state of the system they are approaching is. It's a good idea to wake up and check the forecast before you start decelerating, as you might decide you'd like to bypass that system, if they have nothing you want to trade in or might be hostile, in which case slowing down is not a good idea. But you don't need a very large crew to check that. The crew then individually represents an insane amount of power. In this case, they also have doomsday weapons beyond the ship's own bulk too, and their crew chairs are less places for a junior sailor to park their butt and more like the thrones of kings. And they are entering a genuinely strange place. Say you're departing Tau Ceti, about 12 light years from Earth or some other nearby system, and heading back toward humanity's older worlds. All of the Earth news you had while preparing for the voyage, while taking on potentially high-value trade goods or passengers, see our recent episode on interstellar banking, dated from the year 3000, but by the time that information has crossed the Gulf to Tau Ceti, it's already 3012, and for a short interstellar hop like that, you probably would not climb all the way to Gamma 10 and then slam on the brakes. At 1G, a turret burn, a clean accelerate halfway and decelerate halfway run, takes about 13 or 14 years by outside clocks, while the crew experience is only about 5 years. By the time you actually reach Earth, it's 3025 or 3026, A whole generation has passed. You do receive updates as you approach, with steadily shrinking delays, but your crew, your cargo, and even your assumptions were all shaped by our world a quarter of a century out of date. You may find they are no longer welcome, if the destination system's culture or government has shifted in the meantime. And that's just for your nearest neighbors. Life aboard a relativistic starship means accepting that the universe outside may age very differently from you, but at least everyone aboard still lives under the same laws of physics. In our episode, Outsider Aliens, we push that much further. What if the beings we encounter don't come from another star, but another reality entirely, one with different physical constants, different chemistry, perhaps even a different definition of matter? That's out now exclusively on Nebula, along with our Alien Life collection, gathering 11 episodes on everything from alien languages and synthetic life to giant space monsters and post-consciousness civilizations. Nebula is also where over 800 episodes of SFIA premiere early and ad-free, alongside bonus content and exclusives. Use my link or the QR code on screen to get 50% off an annual plan, just $30 for the whole year. How fast is fast enough? Taken together, these constraints suggest that there is no single correct relativistic speed. Instead, there is a spectrum of trade-offs. Within a galaxy, speeds on the order of 20 to 30% of light speed may represent a practical upper limit for most traffic. Above that, collision risks, shielding mass, and energy demands rise rapidly. Dedicated corridors swept clean by infrastructure might allow higher speeds, but only along carefully controlled routes. Again, that's something we discussed in Interstellar Relays, where the stations along the way can actively scan and remove particles from the travel corridor, sweeping with a laser broom when not pushing a ship with a concentrated beam. Intergalactic travel is a different regime entirely. Between galaxies, matter density drops dramatically. Dust becomes rarer. Big clumps should be proportionally even more rare. Distances become so vast that even modest increases in speed pay enormous dividends. In such environments, truly ultra-relativistic or even near light-speed travel may become attractive despite the risks. For most purposes though, even a tenth of light speed is transformative. At that speed, time dilation is modest, but travel time collapses. Mars becomes roughly an hour-scale destination at cruise speed, though in reality you would never get close to a tenth of light speed on a Mars run, unless you had some unknown inertial dampening system and an alarming disregard for traffic control. At 1G, you would accelerate halfway and slow down long before reaching even 1% of light speed, and again we call that maneuver a turn and burn. The outer solar system becomes a matter of days or weeks depending on acceleration. Nearby stars become reachable within a human lifetime without extreme relativistic effects. It is easy to forget how extraordinary that is. A ship traveling at 10% of light speed is moving 100 times faster than anything humanity has ever built, and yet its time dilations, tau and gamma, are just 0.995 and 1.005 respectively. You gain just 2 days per year of travel at such speed and arrive at Alpha Centauri 44 years later with 80 days off your calendar. It is a good question though, are you celebrating your birthday on a ship calendar or Earth calendar? And for that matter, are you getting paid on the one or the other? Is your bank or your credit cards using local time or ship time for calculating interest? And again, see that Interstellar banking episode for more discussion. But that's just one of many issues relativity brought to our lives rather than just engineering problems. Such modest speeds alone would reshape exploration, commerce, and warfare, even without pushing the relativistic regime. Relativity does not make the universe small, it makes it flexible. It allows travelers to trade time for distance, personal experience for historical consequence. For people like Vitor, that trade is worth it. For civilizations is one more tool, powerful, dangerous, and transformative. And like all such tools, it will not be used lightly.